So this morning we concluded understanding the implications of the conformal group, and we saw that we are starting to encounter various definitions. When you have various definitions, of course, one is a definition, the other are consequences, but when we have various equivalent definitions, it's good. We pick whichever one we like the most. And the one we started first was saying a conformal theory is a theory which is invariant under local dilatations. In particular, this was equivalent to telling how fields transform, what are the transformation laws, prescribing some transformation laws, can be succinctly encoded into this equation for the generating function where these currents couple to the operators. So this was one definition. And then we saw that this implies that 2-point functions are just power laws, 3-point functions are just power laws, and 4-point functions are power law times a function of cross ratio, which can be a very non-trivial function. But even that function of cross ratio I can write as an expansion still in terms of the CFT data, where I sum over structure constant squared times the conformal block for the exchange of a given primary. And therefore, really, all I need is a set of numbers, deltas and c's, and that defines my conformal field theory. So a conformal field theory can also be thought of as a set of numbers which obey the bootstrap equations, which is a kind of a consistency equation. In other words, give me an OPE algebra. Give me an algebra, and if you give me that algebra, I can use that algebra to compute everything. And the associativity, if you give me an algebra, it should be associative, and the statement that the algebra should be associative is the statement of the bootstrap equations. So give me an associative algebra, and I give you a conformal field theory. Of course, there is an even more standard definition compared to these two, which is often I have the luxury of giving you a Lagrangian. And in that Lagrangian, there can be some couplings, and those couplings typically run with scale. And the CFT is one where they don't run with scale, where there is no scale and the beta function is just 0, like n equals 4 super Young-Mills. In n equals 4 super Young-Mills, I gave you a Lagrangian. There is a coupling, G Young-Mills squared, that appears there, multiplying the various vertices. And I can study how does it flow as I integrate out heavy degrees of freedom. How does this coupling change? And it doesn't change. It's a conformal field theory. The beta function is 0. And that's, of course, another equivalent definition of a conformal field theory. I also said that often it's nice to think more broadly and think that we can have conformal theories more than conformal field theories. The difference being basically that one contains a stress tensor. Okay? Now, then we saw already two nice applications of general logic. Let me maybe just finish the summary first. Two applications of this general logic of conformal field theory. One, we studied three-dimensional conformal field theories. We said experimentally, I know that I just need to tune the critical temperature and the magnetization to detect phase transition in a magnetic material. So I have two relevant operators. Suppose someone tells me that the dimension of sigma is around 0.5, 0.6, 0.7, you are not sure. That's enough already because it tells you more or less where to look. And then imposing consistency of the bootstrap, basically the idea that you are summing stuff which is quadratic in Cs and therefore it's positive, you can often reach contradictions and in this way rule out the possible guesses for the spectrum. And in fact, you rule out roughly everything. The size of this island, say in the talk that I was quoting for, which is 2 years ago, was already in the 4th digit. That's how small this island was, which is by far the very best determination of these critical exponents. And here we are dealing with good conformal field theories. Namely, in the OPE of sigma, say with sigma, there is an operator of dimension 3 and spin 2, which is the stress energy tensor. But then we also said, well, now that we have this idea of conformal theory, we realized that, well, a conformal theory I get whenever I put anything inside ADS, in particular a massive quantum field theory inside ADS. Now I use ADS as a box. There's no ADS CFT duality. It's not a duality. It's a box. And I put stuff in the box, and the box induces a theory at the boundary. It goes in one direction. If I put something, I gain a conformal theory at the boundary as a definition. I don't have an alternative definition of this conformal theory. For example, if I put free massive particles in ADS, I get in the boundary a generalized free theory. And in that case, I can define the theory by just saying that the propagators are just 2 weak contractions, and the propagator is 1 over x minus y to the 2 delta. But in general, what I know is that if I compute a massive quantum field theory and consider correlators which approach the boundary, they behave as those of a conformal theory, so they have an expansion in conformal blocks with positive coefficients and so on. And I can use bootstrap techniques once more, but now to learn about massive stuff in ADS. And I told you about an idea, which is, well, but then if I take the box to be very large, which translates into the statement that the dimensions are very large because their mass, the mass of the particles is very large compared to the ADS radius, then we just postulate some spectrum, say imagine like I have 3 masses below the 2-particle continuum, and I run this kind of arguments that we said about the bootstrap to rule out massive quantum field theories in flat space and say that for a given mass spectrum, the coupling that I find in flat space must be at most this big, because if it was any bigger, the particles would become lighter, or I would form more bound states that would come in. Some delta 4 would come in from the continuum and show up here. Right, that's the intuition. And indeed, the numerics work out, and you get some nice plots, and then you can plot the coupling for all physical theories that people measured so far, and indeed, you see that they lie below the plot, as they should. Otherwise, there will be a big problem with this argument. Another application that I did not mention of these conformal bootstrap ideas is to try to understand if there are analytic limits that I could study. Are there limits, for example, people have been studying large spin limits, limits where by playing with these cross ratios, this is localized on configurations of large spin. And there are many beautiful physical things that people have been studying, sometimes trying to look for an ADS interpretation of these operators. For example, I would quote the papers of Jared Kaplan and friends. So everything I've discussed today is very recent. This Kaplan stuff, for example, this kind of papers on large and small operators in ADS is from yesterday. And this stuff on the Ising model is from last year. And this stuff on exploding massive quantum field theories is not published. So it's in the future. So it's more or less recent stuff. As I say, there are some stuff to be done. And but I think it's a fascinating topic on its own to use conformal field theory and the bootstrap as a way of learning about strongly coupled theories. Now, having said that, right now we did CFT. We did this ADS as a box. But ADS-CFT is even stronger. ADS-CFT says that inside the box, there's not a massive quantum theory, there's a theory of quantum gravity. Right? And this is what we argued in the beginning, and n equals 4 super Young Mills is even better. In that case, I really have a duality. I have 2 independent theories, n equals 4 outside and ADS inside. And now that we are ready, we should explore this n equals 4 super Young Mills to see and tell you a little bit about what is the analog and what kind of fun things do we learn about quantum gravity? Okay, that's what I'm going to turn now, but now I can finally take up your question.
So I was just wondering, when you say that CFT is CT plus stress energy tensor.
Yeah, it's not a very rigorous equation, as you can imagine.
No, sure, but so what is the intuition that makes you say that for us to have a local theory, or otherwise, maybe the other way around, if we have a stress energy tensor, that implies we have a local theory?
The idea, if I have a Lagrangian, right? I can couple to it, I can put it in any background if I have a theory, like d phi plus phi cube. I can put it in a given background, vary with respect to that metric that I put, and define the stress tensor, right? Mm-hmm. So a stress tensor is something when the theory will be local, I'll be able to define it. It is just how does my theory respond to changing the background where I put it, right? So this makes sense. Now, you can say, why can't you do the same thing with this generalized free field? You also write dx, dy, you can also try to imagine putting it. You could try, but then when you study variations of the metric, you don't get a local operator, you get a non-local operator. Because you have dx, dy, and variation still will contain one integral. So it will be some non-local delocalized operator that will tell you, if the theory is non-local, when you change a little bit the metric, it is not equivalent to just inserting a local operator at a given point. It's not something, so doing a small dilatation in a theory which is non-local has an effect that is felt everywhere. And it amounts in your path integral to putting an operator which is non-local and integrated everywhere. So
So
it shows that it's very plausible that you need a stress tensor for sure, but it's true that I'm showing it in one direction, not in both.
Mm-hmm. So we might have, in principle, some, let's say, generalized stress energy tensor, but it's not going to be a well-defined local operator, and it just...
Yeah, the example I gave, right? When I have dx dy phi inverse propagator phi, if I imagine I could eventually define what this would mean in any background. Okay, probably I could. So we could define it, right? But then the variation, I take a functional derivative, I get rid of one of the integrals, and the operator will involve definitely taking a point and then integrating over y over all of space-time. Mm-hmm. It's not local, right? It's bad. Mm-hmm.
You also mentioned that beta equals 0 is a definition of the CFT, but that's just requiring for scale invariance, right? Not necessarily CFT.
That's true.
So does this ever come up in any calculations that
sometimes people can show that scale invariance implies conformal invariance. In 4 dimensions, it's an open problem for non-perturbative theories. In perturbation theory, it's established that it implies. Otherwise, yeah, it could be that your theory is just scale invariant. You're right.
So are there big mainstream theories in which we actually don't notice, or
there is no example that people could construct of a theory which is scale invariant but not conformal invariant. More questions? Mm-hmm.
When you write down you introduce these 3 different masses below threshold, mm-hmm. Is it kind of experimental fact or just one of the examples that?
No, this would be an input. For example, it could be an experimental fact. Imagine you tell me that take the Ising model this is about 2 dimensions. We only did this work in 2 dimensions so far. In 2 dimensions, for example, people know experimentally that if you perturb by magnetic field, you flow to a theory that has 3 masses, for example. So this would be like experimental input. The output would be, now I would tell you what's the maximum coupling you could measure. And then hopefully the experimentalists measure and it's somewhere below the curve. Right? Now you could turn it around and ask, can I also start determining, before the deltas were also input, but then I got this island, so it became output, right? So now you can ask, can I start now asking more and more questions and forming islands here and starting to derive masses and couplings of theories and so on? The hope is yes. But this is the beginning of a research direction. That's why it's called explorations, right, in string theory. I'm telling you what people are exploring. This is the beginning.
So is the theory you investigate is 1 plus 2D QCD?
This theory? No. We are exploring the space of all quantum field theories. I'm not saying what it is. I'm saying there is some quantum field theory. I throw it in ADS. And then I just say it induces some conformal theory. The energies inside the box should correspond to the dimensions in the boundary, because we derived it, right? Anything that you put inside the box, the energies of the states inside are the dimensions in the boundary. So what do I expect for the dimensions? Well, there is some M1, M2, M3, and then inside the box I can have 2 particles at rest, or 2 particles moving slightly away from each other, or slightly more, or slightly more. So there is a continuum of 2 particles. If the box was huge, it would really be a continuum. If the box is discrete, it's almost a continuum, right? Because the particles cannot take any momentum they want. They are discretized, with spacing being 1 over the box size. So it's an almost continuum starting at twice delta 1. And delta 1, delta 2, and delta 3, I should take them to be large. So in practice, numerically, we take these deltas to be 10. 10 is already very large. You see the typical delta experimentally, like 0.5 or something. So 10 is huge. Right? Because we want to have, here, we want to have a flat space picture, so the mass times the radius should be very large. Good. Okay. Yes?
So this is the ADS CFT, just a classical picture, right? That the geodesic in the ADS corresponds to correlation option in CFT. Right? So what happens if we consider that quantum level, that the fluctuation at integral ADS?
Yeah, so if you were to consider fully quantum, nothing would change, because the fact that you are getting power loss for 2 and 3 point functions is a consequence of the isometries of ADS. You think that it follows from you might think that it follows from a geodesic approximation, but as I said, no, it follows from symmetry, as we have seen in the CFT. So everything that is said in the CFT translates to correlation functions induced from ADS, because the isometries of ADS are the conformal group of the boundary theory.
I know the symmetries of Greece, but how can we say it explicitly that we compute the both sides? Can we get some, have we got some result already?
For example, you can consider the propagator in ADS. Imagine I consider just a propagator in ADS, right? In flat space, I can compute a propagator between 2 points. Similarly, in flat space, you compute a propagator for a scalar of mass m between 2 points. What do you get? You get some hypergeometric function, something complicated, and so on. Then you take these points, make them approach the boundary, and what do you get? 1 over x1 minus x2 to the power delta. That's the simplest example. Is it a coincidence? No, it has to work. It's because of the isometries of ADS. But it's true that it's a useful exercise to do. So you can take the free scalar that I wrote, and compute a propagator in ADS between 2 points in ADS. It's complicated. It's some complicated function. As the points go to the boundary, I get just a power law behavior as I should.
So it doesn't matter whether it's classical or quantum?
No, it does not. It's purely a consequence of symmetries. Okay, good. So now let's study a little bit. Let's think a little bit. So we have this idea of CFT data, but I told you about the fanciest kind of applications of computing these deltas and these C's and so on. But often we want to do perturbation theory. It's not a sin to do perturbation theory. So we might also have some theory which is weakly coupled, and we want to compute these deltas and these C's using Feynman diagrams, right? And using perturbation theory. So let's try and let's learn a little bit how that works in a conformal field theory, how we start doing this perturbation theory, and let's see a little bit what happens. Okay. Okay. So first, we will compute what are our operators that we are going to study in n equals 4 super Yang-Mills. So here they are. So this is an operator, O, at some point x, which you see, remember what we discussed before. Why should we multiply many of them and take the trace? Because we want to consider gauge invariant operators that don't transform under gauge transformations. And I also remind you that each trace, because it's a trace, it's cyclic, right? I can rotate this operator here. I can always rotate. So it's a cyclic object, which has this pictorial representation of being exactly a closed string. So I have a string and a bunch of scalars getting out, which is the beginning of the cylinder. 1, 2, 3, up to the last one, which is L. Okay? And there were many ways of drawing this. I also like to draw it like this to highlight the double line notation, where even though I'm stretching, all this stuff is at the same point x, this bottom line, but I'm just saying that here I have a scalar I1, I2, up to IL, where I takes values 1 up to 6. There are the 6 scalars in n equals 4 super Yang-Mills, which I remind you, 6 is a natural number because it's the symmetry of the sphere, of the 5 sphere. Right? There is a symmetry that rotates the 6 scalar. Okay? So this operator is this picture here, or this picture here. It's a single trace gauge invariant operator, so it's the good operator that I should consider. They correspond to a closed string. And because there are many operators, because I can choose many choices for these indices I need some collective index A that tells me which I's I'm choosing. Okay? So this A, you see, takes roughly 6 to the L values, right? Because for each scalar, I choose for each index, I choose which one to take. Do you agree? I mean, it's roughly, it's not really true because of this cyclicity. For example, I told you that this is cyclic, so there are many stuff that is the same. But just to get an idea, it's exponential. It's many. Okay? So of the order of 6 to the L possibilities for such operators. Okay, very good. What's the dimension of this operator OA? Right? So what's the dimension of OA? Well, the dimension of OA definitely starts with L. Because if I just connect an OA with another OA and I do a 2-point function, I just consider L propagators. And each propagator is 1 over x minus y squared. So in total, I get 1 over x minus y squared to the power L. Do you agree? Was it too fast? It's okay? Again, I'll draw it. Because in a computation at 3 level, what would I do? I would just take the operator and contract. There are L propagators. So I get 1 over x minus y squared, which is the propagator. And this appears L times. So I read off the dimension, it's L. Okay, this is just perturbation theory. It's just counting the dimension, right? Each scalar is dimension 1. I put L scalars, I have dimension L. But now there can be quantum corrections plus quantum effects. And the first thing I want to point out is that right now we have a huge degeneracy, right? Because everyone here has the same L. So we are dealing with a problem which is a bit unusual, and you probably, if you did not play much with theories with indices like large N, vectors, or adjoint theories, typically you are used to writing Lagrangians where there's like one field phi and then composite operators like phi square and then phi cube and so on. And each of those operators has its own dimension. Now it's a bit different. Right from the beginning, we have a huge exponential space of operators that are all degenerate. All of them have the same dimension, right? So if I take like 10 scalars, there are a bunch of operators of dimension 10, many, many of them, right? Okay. So there is a huge degeneracy. Degeneracy. We will take care of this problem now. So let's start thinking about perturbation theory. And here I wrote the vertices that you can typically have, or that you can have if you consider operators made out of scalars, which we are going to, because we choose it's simple enough. We have a propagator, right, which is 1 over x minus y squared. It comes with the power of the coupling. These are the color indices, and these are the SO6 indices that run from 1 to 6. Okay? Then we have vertices. We have a vertex of the scalars, which is a quartic interaction coming from the trace of phi squared. We have an interaction of the scalar with the gluon, which I drew a double line, right? Which comes from the covariant derivatives. When I write covariant derivative as derivative plus a mu times phi, there is a cubic and a quartic interaction, right? Do you agree? And in fact, the quartic interaction is the same as this, right? This was the origin. All these came from the same 10-dimensional gluons, right? So that's why there is this interaction here as there as well. And then we have this Yukawa type of interaction that a scalar can split into 2 fermions. Okay? That also came from the fact that the fermions have a covariant derivative in 10 dimensions that couples them to the 10-dimensional gluon. And the scalar is like a 10-dimensional gluon. Okay? And there are 6 scalars because there are 10-dimensional gluon, and 4 become 4-dimensional gluons, and the remaining 6 become the scalars. So these are our rules. And now using these Feynman rules, we start drawing planar diagrams. Only planar. We are going to do the planar limit. We are going to study the limit when n goes to infinity. So we want planar graphs only. Okay? So we start drawing planar graphs, but now I will not use double line. You see, here I already did not use double line. I already lodged a single line because double line takes too much time to draw. Okay? But let's start drawing some diagram that can appear. So I can draw the 3-level computation. I just connect everyone. Right? So here, for example, if I have some index I1, and here if I have some index J1, the indices need to be the same. So there is some delta I1, J1. Right? I need to identify the scalar. The propagator only connects scalar of the same type. And then here, for example, I could have a fermion loop. Right? I could have a fermion loop. Or here, okay, this line, so I have the fermion loop. Now I focus only on this line. I could have a fermion loop plus I could have some gluon exchange plus etc. So these diagrams involve a single line. And then there will be diagrams that will involve more than a single line. Let me draw here again the full thing. For example, when the lines throw a gluon at each other. Okay, so these diagrams involve line at position j and j plus 1. So this involves 2 lines. And also, for example, another diagram that involves 2 lines would be when the scalars interact through this quartic vertex that I drew there, right? So this is the quartic interaction of the scalars. And this also involves two lines. And there could be a bunch of other diagrams that would involve two lines. Actually, these are the only two. Okay, if they involve two lines, it's just this. If they involve one line, there are a few more diagrams like this. Okay? Okay. So now this one here is the most interesting one. And I will start by this one. And then I'll tell you why actually this is the only diagram we worry about and why I can actually more or less ignore all other diagrams, even though there are still some comments that I want to make about them. Okay? So let's study this diagram here and see what happens here. Okay? With this diagram here. So with this diagram here is proportional to what? Let's write what this is. So this gives me delta I1 must be equal to J1, I2 must be equal to J2, I3 must be equal to J3, right? You get the points. And then you reach a point where you are at position n and then plus 1, right? At position n and then plus 1, there will be something that I'll leave here some space to write. This is related to position n and n plus 1, and after I continue delta I n plus 2, j n plus 2 must be equal delta I L j L. Okay? So from the point of view of indices, these diagrams are 0 unless most of the indices are the same. Okay? Now, what about this diagram? So this diagram, there are various factors I should write. So the first factor I want to write is what is the integral itself. Let's forget about the indices, but what integral should I do? So let me write it. What is it? So I have an integral over a middle point, let me call it d4z. And then I have two propagators from the bottom to point C and two propagators from the top. So I have 1 over x minus z squared times y minus z squared, and it's two propagators, so this all is square. Right? I have two propagators. So this is the diagram I have to compute. I have to do this integration over this midpoint to see what I get. Right? So speaking of dependence in x and y, let's notice I forgot to write that then there is still here 1 over x minus y to the power L minus 2. This delta function comes with its own propagator going from bottom to top. Okay? So, sorry, x minus y squared, and this to the power L minus 2. Okay? So from the point of view of x and y, I'm done. It's the L minus 2 propagators and this graph here. Okay? Now it comes multiplied by some index structure. So let's think a bit about this index structure. This index structure comes from this interaction trace of phi I comma phi j square, right? Which is equal to trace of phi I, phi j, phi I, phi j minus, with a factor of 2, minus 2 trace of phi I, phi I, phi j, phi j. Right? So if I want to think what this gives me, it tells me that from the point of view of indices, if I use colors to follow the indices, I have the possibility of the index being swapped. So this would be, coming from the first diagram, tells me that I have I, j again. Now I'm drawing the color index, the 06 index, sorry, not the color ones, of course. And I also have the possibility here, this diagram, so this would come, say, with a factor, overall factor I don't care, but I want to point out 2, for example. And then there are two possibilities. There is the possibility here of saying that I have I that goes into j, and the same vertex seen from the side, I have the possibility of I, and here jj. Right? And because this vertex gives the two possibilities compared to this one, this just comes with the coefficient -1 and here -1. Okay? So this stuff here comes here. So this means this stuff goes here in this parenthesis here. Where by this I mean what? So let me write it here, sorry. By this I mean that I have delta. So the first term is a 2 times delta. In goes to jn plus 1. Delta in plus 1 goes to jn. This is when they get swapped. Minus delta, the second term, in must be equal to in plus 1, and then jn must be equal to jn plus 1. And then there is minus also a final term when delta in is equal to jn, delta in plus 1 being equal to jn plus 1. Do you agree? Okay, and on top of that, there is an overall, there will be a 't Hooft coupling lambda, once I keep track of all powers of n, because as we know, in the large n limit, in the end, everything becomes powers of 't Hooft coupling when normalized properly, right? Compared to 3 level, of course, depends how I normalize 3 level, but the relation to 3 level is 1 lambda, and eventually some number. But the number I don't care. Okay, so this is what we get. Okay? So now let's analyze the various bits and pieces. So let's study a little bit what's happening with this diagram here. Okay? So let's see what happens with this diagram. Okay? And what happens is the following. You see that when z approaches x, this looks a bit dangerous. Because when z approaches x, this diverges. It blows up. It's a UV divergence. The point z approaches the point x, things is blowing up. So let's study the region close to z equal to x and close to z equal to y. Of course, there is a symmetry. So they just give twice the same thing if I just zoom in close to x. So let's zoom in close to x to see what this gives. It's the most important contribution because it's when this thing becomes very big. So if we zoom in close to x, if z is close to x, so let's say z close to x, here when I have y minus z squared, I can just replace this by y minus x squared. This term is regular, and I'm focusing on the singular behavior. Here I can replace this by y minus z squared. So I do it, and I say, so this is approximately equal, and here I put y minus x squared square. Okay? This is nice, because there was here a -2, and now there is here a +2. So together, they are combining into the power L, which was the power that we got at 3 level. But then, on top of that, okay, so this 2 is nice, so we like this 2, because it's +2 and -2 here, so this is good. But then on top of that, we have integral close to x, and now because I'm close to this point, I'll shift coordinates and consider that here is x, here is y, and I'm considering coordinates, spherical coordinates around this point. So z is x plus w, right? So I'm considering coordinates adapted to studying the neighborhood of this point. So what I get is d4w over w squared squared, right? So if I go to radial coordinates, this stuff will be equal to just some number times the integral of omega cubed d omega over omega to the 4. The number is the volume of a d sphere, right? And this is 1 over omega, it diverges logarithmically. So it diverges logarithmically, and what should I use for my cutoffs? Well, UV cutoff, I will use some UV cutoff. I'll say that W can go up to some UV cutoff, 1 over lambda, some UV cutoff. What should I use for my infrared cutoff? Because this diverges at small w and large w as well, right? But large W is a fake, because this approximation is true if I'm far away from Y. So the infrared cutoff, I should use some number of order 1 times the distance Y minus X. Right? Some, I don't know, I can stop in the middle between X and Y. Okay?
Would you please move forward?
Okay. So the conclusion is the following. We considered a correlation function of two operators, OA, OB, and here is what we got. We got at tree level 1 over X minus Y to the power 2L. Right? This was the tree level result. And then we started doing loop computations and we got the following. So at tree level, the operators had to be the same. So there was some delta AB. At loop level, however, what we got is that the operators don't need to be exactly the same. So let me parameterize the difference by saying there is a matrix H AB. The indices AB now can be different, not very different. Most of them need to be the same, but at position n and n plus 2, they can be slightly different. Right? So A and B can be slightly different. They can differ by swapping a few indices locally. Right? I will normalize it such that lambda I put outside to emphasize that there is a quantum effect. This is a one loop effect. And the integral then gave me a log of lambda square times x minus y square. Okay? Plus the other diagrams. Okay? This is what I want to point out. Okay. So this is what we are getting. Any question here? Now, this is very general. Whenever you have a CFT with some degeneracy, this is what you will get. You will compute the correlation function of two operators. They will be degenerate. And then you can get typically logarithmic divergences that, as I will now explain, are related to multiplicative renormalization of the operators, so which is the usual thing. Okay? As we will see, it's crucial, it's needed if I want to get quantum corrections to the anomalous dimension. This is just how it works. Okay? Any question? Any? Yeah.
The x minus y squared is inside the node, right?
Yes, yes. See, it's a dimensionless quantity. Mm-hmm. That's a good point. Well, let's see. It looks a bit weird. This doesn't look like a power law. But how could we get a power law? The propagators are just integers. How could we get non-integer powers? So I'm going to explain now. Naively, it looks a bit weird. This does not look like the two-point functions that we fixed by symmetry, right? But that's fine. That's a normal thing. I will come back. More questions? Okay, so now before we continue here, I want to make a few comments on So the comment I want to make is the following. This delta AB, we computed, and we saw it's given by a number. Okay, a number. Times. Then I want to rewrite this thing. Twice this graph, which swaps them, minus this graph that annihilates them, okay, minus the graph where they get swapped like this. Okay? And I want to point out that these two graphs here, they change the indices, and this one does not. Right? So this is diagonal. So this is like this. Right? This, together with all other indices, finally, I have said that A is equal to B. Okay? Now, the first comment is that all other diagrams are diagonal in this sense. All other diagrams, just by conservation of color, for example, the ones with a single line, a scalar of a given color comes and leaves, of course it cannot change color. This color is a symmetry. Right? And indeed, you can see the gluon doesn't carry color. If you see the Feynman diagrams, if you follow the Feynman rules, you would see that whatever comes in gets out. Okay? It must be just an SO6 symmetry. Also, when you have these two lines and they exchange a gluon, because again, gluon doesn't carry charge, doesn't carry SO6 charge, so it cannot change. So whatever these diagrams give, all these other diagrams, they can change this number here. Okay? But as I will explain in a second, this number is not important. So that's why I said that we only need that graph. Okay? So this is the potential thing that the other diagrams could do. Okay? The second comment, so this is comment number one. The second comment is that, in fact, if you study diagrams, say like this, they are not log divergent, they are power law divergent, which is much worse. Power law divergences indicate that you have to renormalize the mass of your particles. It's the kind of diagrams that you get when your mass needs to be renormalized. You start studying your propagator, and you start seeing that you get some counter terms, and you need to renormalize. Now, these are much more problematic, because I said the theory is a CFT. This I definitely cannot have. So these guys, this is a fermion. It comes with a minus sign. And these guys, they cancel by supersymmetry. Right? So all these one-leg diagrams, it's a nice exercise to see that when I add them all up together, indeed, the quadratic divergences vanish, and I'm left with just the log divergences as I expect for a CFT. Okay? This is because fermions and gluons and scalars, they come with different signs, and of course, it must work, and it does work that they cancel. Okay, so now let's go on. So now we take this formula as our starting point. I have some CFT, and in my CFT I computed, I can now cross out the other diagrams because they just renormalize against the diagonal part, and I got this result where the 2-point function was a power law plus lambda times the log divergence. So this, as I said, is generic. Any CFT with some degeneracy, this is what you will get. Okay, n equals 4 is just an example. Now let's do the following. Let's define O prime to be equal to a linear combination of psi A times OA. This guy here, I will call it wave function. These are a bunch of numbers. Okay? And I'm considering a linear combination of these operators which diagonalize. I consider this combination to diagonalize this matrix HAB. Okay? So if I act with this matrix H, if I think of this as a matrix H that gets me an operator and sends me into another operator, I'm saying consider a linear combination which is diagonal. Okay? I'm considering a matrix such that H acting on O prime, right, will be equal to some gamma times O prime. Okay? And there are many operators. This is a big matrix, right? So this, I remind you, is a 6 to the L times 6 to the L matrix. So there are many such eigenvalues, so perhaps let's put an index n to indicate that it's one of them. And then, okay, we have H times On is equal gamma n times On. Is it okay? So I just choose a linear combination. Now, once I did it, and I go to this equation, what I'm getting now is that On of x, M of y will now be proportional to delta Mn over y minus x squared times 1 plus minus gamma m lambda times log of lambda squared x minus y squared. Okay, so I diagonalized my problem. So now I just have a number which is the eigenvalue.
Should it be 2L? 1 minus x is 2L?
Yeah, it should, yeah. Right? You agree? Okay. So now, finally, the problem, the matrix part disappeared because I diagonalized this matrix. I can focus on one particular guys. I can put n to be equal to m, and now I have just a number equation. There's no matrix anymore. And notice that this factor here, this is nothing but 1 over y minus x to the power 2 lambda gamma times 1 over lambda to the power 2 lambda gamma. If I expand this at small lambda, I get 1 plus this, exactly. Right? So what do I conclude? I define now one more thing. I say, well, but then let me define On renormalized, my renormalized operator. What is my renormalized operator? Well, I say it's cut off to the power lambda gamma n times my operator On, which was my bare operator. And the claim is that this operator has the correlation functions that On renormalized, Om renormalized are equal to delta Nm over x minus y to the power 2 delta, where delta is L plus lambda gamma n plus 2 loop quantum effects if we were to compute further. Okay? Do you agree? So the conclusion is that when you are given a conformal field theory, what you should do is study 2-point functions and look at the log divergence, at the matrix that captures the log divergences. All you need to do is compute a 2-point function, identify the logarithmic divergence to read off a matrix H, which is called the mixing matrix. Take that matrix H, diagonalize it, and when you diagonalize it, you get operators with good anomalous dimension, and you also get the anomalous dimensions of the operators. Okay? So you reduce the problem of computing the anomalous dimensions to the problem of diagonalizing your mixing matrix H. So now let's see, what is this mixing matrix in n equals 4 super Young-Mills? Sorry?
I mean, this technique seems to be very generic.
Yeah.
It's not necessarily working for the CFT only.
That's true, yeah. In the CFT, there is a one-to-one correspondence, renormalization and anomalous dimension is the same thing. But in general, you also have to multiplicatively renormalize any composite operator in any quantum field theory to have finite correlation functions. You see that all we did was say, this operator, this is the operator that has now finite correlation functions. Now if I compute expectation values of any n-point function of these guys, it's finite. Otherwise it's not. If I consider of these guys, it's almost the same thing, except that I get the power of cutoff, right? So by the way, let me remind you, before I move on, when you study this geodesic example, when you studied the geodesic example, you saw that this geodetic, it was proportional to what? To x, but it was not just x to the m. You had x to the power 2 delta, but you had here epsilon, which was some cutoff to the power 2 delta, something like that, right? And this epsilon was from cutting somewhere at some distance epsilon from the boundary. And you see it's exactly the same thing. I take this epsilon, move it to the other side, define renormalized operators such that they have finite expectation values. This is exactly the analog of doing this renormalization, but from the ADS point of view. Okay? So this was the homework. Okay, so now I want to point out that this matrix H is a special matrix. Even though it's a 6 to the L by 6 to the L matrix, it's a very sparse one. Because only indices which are nearby can change. Why only nearby? Because we need to be in the planar limit. So you cannot have a propagator jumping and interacting with indices that are far away. But then physically, we can actually, it's just for our own convenience, psychologically, we can translate this problem into a quantum spin chain problem. So we can do the following translation. I can say that, let me think of in the following way. Trace of phi I1 up to phi IL. Let me think of this. This is a 6 to the L to 6 to the, it's an object with 6 to the L components. Let me think of this as the ket I1 up to IL. Right? I can make linear combinations of this guy. I can make linear combinations of this guy. It's just notation. Okay? Then I had, this was my operator OA. And I had a matrix HAB, right? That would act on this, on this index here, rotating my operator, right? Right? And now I can translate this into a language of an Hamiltonian that acts on my spin chain. So this is an SO6 spin chain. I can think of this as an SO6 spin chain, where at a given site of my spin chain, I have some A, which is an index that runs from 1 to 6. And I have L sites. And then I have an Hamiltonian, now an Hamiltonian, that acts on my spin chain. How? Well, it is proportional to lambda times the number. That's the strength. Then it can act in any position of the Hamiltonian with some Hamiltonian density that just acts on position n and n plus 1. And what is this Hamiltonian density? This Hamiltonian density, n plus 1, is twice p minus k plus a number that I did not compute for you times the identity operator. Where what are these operators? This p is the permutation operator that acts on AB and gives BA. What is the identity? The identity acts on AB giving AB, does nothing. And what is the trace? Trace acts on AB, and if A is equal to B, gives me a sum from C equal 1 up to 6 of CC. So in pictures, this is the permutation, this is the identity, and this is the trace. So do you agree that the problem we saw there, diagonalizing, now what we want to do is take our spin chain, act with some Hamiltonian, and find what are the eigenvalues of this spin chain Hamiltonian, and L plus gamma, the set of L plus gamma, is the set of dimensions of n equals 4 super Young Mills. I mean, at one loop, of course, and for scalars. Okay? Right? So it's kind of fun that we translated a problem of four-dimensional quantum field theory into a problem of diagonalizing one-dimensional quantum spin chains. Right? So the kind of problems that Giffre has been telling you exactly how to solve throughout these lectures. Okay? It's still not a trivial problem because this is still a 6 to the L by 6 to the L matrix. So it's still complicated. Except that that there's something quite remarkable, which is that you can go to the books on Hamiltonians and ask, are there special Hamiltonians? Okay? Are there Hamiltonians that are easier to solve than others? Okay? These are called integrable Hamiltonians, or exactly solvable Hamiltonians. Hamiltonians that I can actually compute a spectrum analytically. Okay? And now it turns out that there is something absolutely remarkable, which is that the ratio of these coefficients here, you see, okay? This ratio should be -2 for an SO6 integrable spin chain. Exactly if this coefficient was -2, if the ratio was -2, which we derived, the spin chain would be integrable and exactly solvable, and you could actually compute its spectrum and solve it by means of techniques known as Bittensatz and thermodynamic Bittensatz. So it's kind of a present, it's a gift. It looks like really a miracle that we just compute this and see that we get a one-dimensional spin chain. That's already nice. It's much simpler than to deal with 4 dimensions. But we don't get any one-dimensional spin chain. We get, within the space of theories, we get precisely the ratio that makes such that this theory is integrable. It's really kind of a miracle or a gift. Who gave us this gift? Well, it's anonymous. We don't know. But actually, it's not very well disguised. We can find out who gave us this gift. So why did we get this gift? Well, because the coefficient was -2. Why was the coefficient -2? Because it was a commutator. So from that commutator, the structure of the commutator is such that right away any theory with a commutator will give a -2. So the -2 was just because it was a commutator. And the commutator is there because it comes from a compactification. Because any compactification, as we said, when you compactify, the scalars get this commutator interaction. So it looks like provided we compactify, we would get -2. That's true. But we don't want just -2. -2 is what you want if you have SO6. If you have SO5 or SO7, it's already another number. So this is good because 1, we have the commutator, and 2, we have SO6. So it means that it's good because we compactified, but we compactified down to 6 scalars. So which means that we came from 10 dimensions. So obviously this is a gift from string theory. Right? It's really smelling like it's because there is some 10-dimensional string theory, and it's telling us, okay, look, here's a gift, so please pay attention. And this is a small observation that was the beginning of an explosion in activity in n=4 super Yang-Mills, that once people understood that, wow, this is quite amazing, I'll be able to compute these anomalous dimensions exactly, and this was just a subsector. This is just scalars, and it's just one loop. But it's already such a remarkable miracle that from there on, people kept exploring, considering more operators, more loops, more this, more that. And that's the beginning of a big field, and I don't want to go in that direction, but I can just tell you that it's one of the big investigation programs and one of the ones that I'm very involved in, which is exactly solving n=4 super Yang-Mills. And this was the first smoking gun saying that such crazy thing could be possible. And right now we believe that we will indeed solve n=4 super Yang-Mills and we will have a full solution. But this was the first critical observation by Minahan and Zarembo in 2003, hinting that such thing could ever be possible.
Is there physical justification for 4 supercharges, or is it just because of this reason that you consider n=4?
Why we consider n=4 super Yang-Mills?
No, I'm saying, is it more than that you can just solve it, or is there physical justification also for?
So n=4 super Yang-Mills, we did not choose it, right? It came from the brain construction, right? We saw that n=4 super Yang-Mills is the theory that describes the low energy degrees of freedom on the brains when we followed the decoupling argument. So it was not our choice. It was not like I could, right? So it came naturally. Now, what we are observing here is that there seems to be something special. And there is some exact solvability of these spin chains, indicating that I might be able to compute the spectrum of this quantum field theory exactly. Even in this example, it was all numerical. But here it seems like it's a 4-dimensional quantum field theory, strongly coupled. And at least I'm seeing some signs of exact solvability that I should definitely explore more and see where it leads me. And it does look like it comes from string theory. So next what people did is, wait a moment, let's see if I find some integrable structures on the string theory. So this is one of these examples that I said that often you use ADS-CFT as kind of a hint, as a helper of guiding you. You do this computation, and then a question pops out. Let's see if string theory is integrable, because at weak coupling it is. Is there some sign of integrability for classical strings now? That means that if I study the equations of motion of my string, Do they have many equations of motion, many constants of motion? Do they have many conserved charges indicating that something special is? So then you say, people, okay, let's try to look at that. Can we construct infinitely many conserved charges for the string and so on? And you go and indeed, you find that the string sigma model in ADS 5 times S5 is integrable. But then, once you find it, you think, well, but this cannot be a coincidence. I start with a theory which is classically integrable, my string theory, right? In the regime where it's classical strings. And I know that in the regime where they are super quantum, I recover integrability again. But then you say, well, but then probably this is a symmetry that is preserved all the way down at the quantum level. Otherwise, it will be a coincidence. I start with this miraculous extra symmetry, I lose it, and then it emerges again. It's a bit unlikely. So then you conjecture, well, but then I conjecture that the theory is integrable and exactly solvable at any coupling. So it means we must be able to solve it. And of course, then people get motivated and start studying quantum effects on string theory, quantum effects at weak coupling, indeed verifying this expectation, and again being guided by bouncing back from one to the other, and learning more and more and more, until the problem of computing the dimensions of any operator at any value of the coupling is completely solved. And this today is a problem that is solved. And I'm not giving you all the story. It took many, many years, but this problem is solved. So I want to tell you about a couple of things that we learned from the solution to this problem. Yes?
Is that solved to one loop or an arbitrary one?
It's solved at any coupling. That's why I put a lambda here.
The integrability here is, the solving h of n plus 1 is just solving for the weak coupling, right? So
here it's just one loop. This is a hint at one loop. Then there is a hint at strong coupling. And then there is the intermediate story, which will take me one more week. But okay. But this is the hard part in a way. You know, when you see that something is beautiful and there and true, and it's some message that it's a very trivial statement, but I heard from a very nice interview that Nima Arkaniamed gave once, and he said the following. If once you are close to the truth and working hard, the truth is an attractor. So you work and you spiral and you get to the truth. And this is one example. We see this, oh wow, it's integrable at weak coupling, it's integrable at strong coupling. If I have enough energy to work on this problem, I'll solve it. It's one of those things, okay, it's bound to be solved now. I am in the basin of attraction. And indeed, people work, and this problem now is solved. Okay, so was there any other question? So let me tell you very simply. I want to make two comments. One comment about. So now we can ask. So if I vary the 't Hooft coupling, and I consider the dimension of some operator, how does it change? Okay? It starts with L, some integer. This integer could be 4, if L is equal to 4, for example. An example. Right? It starts at 4. And now it has quantum corrections. Right? Now it depends. For example, there are operators actually that stay at 4. It's not a very exciting curve. There are such operators. For example, if I do trace of phi1 plus I phi2 to the power 4. This operator, for example, is an example of an operator that stays at 4. But most operators don't. Most operators, they start and they grow, and here they behave as lambda to the 1/4, and they diverge. Okay? So this is an example, two operators, but now I can draw many, many lines. And the point of view, what people find is that most lines go up, and a few stay down, a few stay of order 1, and most grow as lambda to the 1/4. Most states. Okay? So this is the outcome. And this is really beautiful, because what is happening here? What's happening here is that we are increasing the string tension. And as we increase the string tension, what we expect is that each of these objects is like a string, and its mass is proportional to the string tension. So as the string tension increases, these guys should become very heavy. And indeed, this behavior is exactly what you get. This is nothing but a spectrum of flat space. Because the tension is huge, and when lambda is very, 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 very huge, you just reproduce a small vibrating sting moving in the middle of ADS. Exactly as predicted from flat space. So if you go to the lectures and see what is lambda, you can see that this combination is just 1 over alpha prime, which is the way string masses scale. Okay? So this is exactly as we would predict from string theory. However, in string theory, the exception is if you consider massless modes. There are a few massless modes that stay massless, that are like gravitons or something. Those guys, their energy is of order 1. It is just the dimension of like the stress tensor, which is dimension 2. For example, there will be a line here, or no, sorry. For example, there is another operator here on top of this guy, which is t. T mu nu as dimension 4 all the time. It's there. The T mu nu being there and 4 all the time, it's good. It's just that the graviton is there and it's a massless mode all the way. There are more guys though, which are massless. Why? Well, because we are not describing pure gravity, we are describing supergravity. So there are 2 sources of extra guys there. One are gravitons, but gravitons that were moving in the sphere. When I Kaluza-Klein reduce, remember I told you that you can always Kaluza-Klein reduce the sphere and focus just on ADS. But as you do, there are some modes that were before gravitons from a 10-dimensional point of view that now look like other massless modes in ADS. This is an example. This would be a graviton moving in the sphere. And as I Kaluza-Klein reduce, it gives me a graviton from the 4-dimensional point of view. So there are more than the usual gravitons. And also because I have supersymmetry, I don't have just gravitons, I have gravitinos and so on that come together, which are the supersymmetric partners of the theory. In other words, when I do ADS 5 times S5 at low energy, I find a bunch of massless modes, which are the 10-dimensional gravity plus its super friends. And those are the ones that stay here, and everyone else decouples, indicating that I generate that the strings behave as they should, and that I get, therefore, at low energies, just a theory of quantum gravity with everything else decoupled. And I get just supergravity plus nothing else. Okay? So it is just a realization of our intuition seen in a very concrete way, how we start with something where I have a huge degeneracy of 6 to the L operators, big, 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 big degeneracy, and then suddenly I get a few ones here, and everyone else goes up and disappears. Exactly like when we see in a room, we have just the lowest degrees of freedom, right? Like the photons that are coming from you to my eyes, and the gravitons and so on, and we don't see string theory, right? The string modes are very, very heavy. Okay? So this is beautiful, and it's fun to see. There's no phase transition. Things go smoothly. They match exactly what we expect. They confirm exactly the intuition from ADS CFT. Okay? Now just 2 comments. One comment is that once we study the anomalous dimensions, the next interesting problem to study are the 3 dimensions, the 3-point couplings, and even the 4-point functions as function of the coupling, and now they also depend on Z and Z bar. This is one of the active topics of research in N=4 super-Yang-Mills right now. In the same way that computing dimensions of operators is related to dealing with energies of spin chains, now you can imagine that if you want to do a 3-point function, you have 3 spin chains, and what you want to do, you want to cut and reglue them as a pair of pens. So it's about cutting and gluing spin chains. This is something very exciting because there are no tools that are developed. It's not like Giffre was cutting and gluing spin chains as a pair of pens. So we cannot just go and borrow methods from condensed matter. We have to develop new tools for studying how to cut and glue pair of pens into spin chains into pair of pens. In other words, how to study integrable theories on finite topologies and so on. And this is an area of research that we have been making progress of and that I think will be solved eventually because, again, we are spiraling and I think we are in the right basin of attraction. And finally, to make contact with what we said before, you see that now we could go back and ask how does this connect with this stuff, for example. And again, to see a better connection, it will be very nice when we will start studying correlation functions of 4 points and higher in N=4. understanding better this emergence of locality in the bulk, and so on. But one thing we can say is we could forget now about n equals 4. We understood, we learned how gravity appears, and then it decouples from everything very massive, and so on. And let's try to be ambitious and construct a theory of quantum gravity. Okay? So what would be a theory of quantum, again, this is personal opinion. What would be a theory of quantum gravity? A theory of quantum gravity is a theory that behaves more or less like this, but without the extra sugra junk. I don't want this supersymmetric stuff. So what do I want to do, to find? I want to find a CFT where at low energy I have the stress tensor, because I want the gravitons in 4 dimensions. And then I want a huge gap till the next operators. Okay? So now it's a mathematical question. Is it possible to solve the bootstrap equations having a stress tensor as a low-lying state and then a huge gap until the next string modes? Okay? If you construct such theories, I think you have a theory of quantum gravity. You constructed a theory of quantum gravity. If you prove it exists, well, I'm not surprised. I think we can indeed put our universe inside a box, so it better exist. If you prove it doesn't exist, it's also interesting, because then you would have to explain why doesn't it exist. You might show that consistency of the theory to have this big gap. Imagine you show that to generate a big gap, you need supersymmetry, because it's the only way that right now we could generate huge gaps. There's no example that is known where we don't have supersymmetry and we manage to generate this gap. Then you prove that supersymmetry exists in nature. Then it's just a question of waiting till someone detects it. But I will take this as a proof. Anyway, this is just some crazy speculations, but if someone is mathematically oriented, I do think that one of the most fascinating problems in physics is understanding whether there exist conformal field theories with big gaps. Okay, any question? Yes?
So what do you mean by solving this structure constant analytically or just by observation?
No, I don't have any preference. I mean, this plot was solved analytically in the sense that we reduced it to a set of integral equations that then we solved numerically. I mean, by solving, I mean understanding what's going on, understanding the physics, whether to generate a plot, it's analytic or not. I mean, yeah.
I mean, is it possible to use integrable spin chain to solve that, to give an analytic expression, or it was mostly on just like scaling dimension structures?
Yeah, it is. It is possible. For anomalous dimensions, it was solved in 2009, and it has been developed further now over the past years. Kazakov and Gromov and others have been developing it even further. But the problem was roughly solved in 2009, and for 3-point functions, I think there was an important contribution last year, and I think over this year, it's going to be developed. Say in September, for example, I'm having a conference in São Paulo in Brazil, where we'll have like 30 people that are working exactly on this problem, getting together and discussing what has been done and what do we still need to do to finish solving this problem. So I think it's going to be solved soon.
But there are also some non-local objects
Okay, very good. So, given that you asked this question, I'll spend 45 minutes talking about Wilson loops. Okay, very good. So, which was the topic of the talk? I was thinking this would take me 10 minutes. Okay. So, no, I will not. I will probably take 15 minutes. 15! That's 15! It's not 45. It's 15. Okay. Okay, so I'll discuss. I want now to tell you something about Wilson loops. Okay. So why Wilson loops? Wilson loops is a nice example of a non-local observable in gauge theories. So the Wilson loop, W, is the path order exponential of my connection along some loop gamma and taking the trace to make it gauge invariant. So you studied the mathematical definition of this object in the tutorial, right? So you know it is just defined like this. Okay? So today, let me make a few comments of some basic things, basic places where Wilson loops show up. And tomorrow, we will use this intuition of understanding where the Wilson loops pop up in physics to propose a simple dictionary for how we should expect Wilson loops to be described in ADS-CFT. And then in the tutorial tomorrow, we will play with that definition. Okay. So the first place, one natural place where Wilson loops appear in a very nice way is when I study the propagation from a point X to a point Y of a particle in the presence of a chromodynamic gauge field A mu. Okay? So let's first do it without gauge field, and we add the gauge field at the end. So without gauge field A, what I want to do is consider a propagation. So I have my propagator, and I want to propagate from point X to point Y. Well, what is this? This is equal to the integral dt propagation to the point Y, e to the minus t box plus m square. Right? Box is p square. I can put here p square x. Okay? So I'm studying just the propagation from one point to the other. Okay. And now, what will we do? We will get here and say, well, let me decompose this in e to the minus delta t times p square plus m square. And let me do it many times. Okay? So I'm deriving a path integral representation for this object. And now, in between here, we insert the identity operator. And we insert the identity operator as the integral dpi of pi pi. Okay, I insert the resolution of the resolution of the identity there. Good. So then, I just want to use now, then the last thing I will use is that if I have p e to the minus delta t, p square plus m square, and here I have pj plus 1. So I use at each step, I use a different pj. How would we compute? This exponential can get out as a number because it acts on, say, pj, for example, so it gets out e to the minus delta t, pj square plus m square. And then I get p with p, and to compute p with p, I write this as an integral dxj. I insert a complete basis now in x space. Okay. And I write, therefore, the full thing as, and then, okay. So this becomes integral dxj e to the I xj times pj minus pj plus 1. Okay? So in the end, in total, I'm doing it very fast because it's something that I'm sure you have seen several times or you can easily do. But in the end, what we get is the following. We get integral dx1 dxn, integral dp1 dpn that we use to discretize. We use one identity and one p at each position. And then we get e to the minus sum of delta t pj square plus m square plus I xj pj plus 1 minus pj. And now it's quadratic in p, so you can integrate over the piece. And when you integrate over the piece, you conclude that this propagation is equal, and you take the continuum limit to the integral over all x's of e to the minus the integral of x dot square plus m square d tau. From point x of 0 equal x to point x of t equal at the final point equal y. So I should sum over paths like from x to y. Okay? Now, in doing this, what we did here was not the nicest thing, because we had time, and we discretized it in equal spacing, right? But more generically, I could have chosen to put more tick marks in a place and less tick marks in another place, and I could choose some density of t's, right? That would be a bit better. So the best thing to do is to introduce some metric, E of t, that transforms, which is like a metric that tells me what's the density of tick marks, okay? And if I were to do it like that, I would, here it will be over E and here times E, where E transforms in a way, E goes to f prime of t times E under t goes to f of t, such that that object is invariant under changing a parameterization, such that the parameterization is not important. What matters is the path. Okay? And then nothing depends on E, and I can integrate over E. And when I integrate over E, because E has no derivatives, E is not a dynamical field, I can eliminate it by its equations of motion. Whenever you have a field that doesn't have a kinetic term, in practice you can eliminate it through its equations of motion. So what we conclude is that the propagation from point x to point y is the integral over all paths e to the minus m times the integral of square root of x dot square d tau, and this is nothing but the length of the path. Okay? And by the way, I remind you that when the mass becomes large, it becomes e to the minus m times the length of the geodesic, which was what we used in the exercise. Right? Yeah? Okay. Now the point is that if you see now, with a gauge field, right? All you should change P to P plus I times the gauge field, right? You agree? This minimal subtraction stuff when you couple to a gauge field. And in the presence of the gauge field, almost nothing would change. You would have now the gauge field, and the gauge field that is now a matrix, right? So now when I think of this propagation, I should think that I have a quark, which is a vector, and it propagates by multiplying by many matrices. At each point in my path integral, I should put e to the IA, e to the IA, e to the IA, here and here and here and here. Whenever I derive, whenever I use this, whenever I have P here, right? I put P plus A, but I have to multiply it as a matrix and keep the order. The first A, second A, third A, and so on and so forth. Do you agree? So what happens if you follow this carefully is then that what you get is that the propagation from x to y becomes equal to the integral over x e to the minus m square root of x dot square, which is the length, times the path order exponential, which is the Wilson line along the path gamma, if this is gamma, where this is the path order exponential of the gauge field from one point to the other. Okay? Is it fair? I mean, I don't, yeah. Okay. If you want more details, pass by at the end and I'll tell you more. Okay? So we conclude that the Wilson line, if I want to describe particles in this way, which is a nice way of summing over paths and so on, which is an equivalent way of talking about particles, right? If I want to describe this, some people call this first quantization. If I want to describe particles in this way, when particles propagate, I sum over the path with e to the minus the length of the path. But when there is on top of that a gauge field, I should weight it with a Wilson line. Okay? I should weight it with a Wilson line that goes from point X to point A in a path ordered way respecting the order, which was one of the definitions of the Wilson line. Okay? So that's what you would get if you follow the definition. And this is parameterization invariant, and so is the Wilson line. So in total, you have a good object, right? So this is something that you are very familiar with from almost high school when you studied QED and the Hara-Nombom effects, right? When you study the effect that if you have an electron and the electron goes through one side or the other of a solenoid, right? That it picks a phase by going from one side or to the other, and the difference, which by difference I mean that the difference in phase is the integral of a mu. Now it's in QED, this is an electron. So this is really a number now, it's not a matrix. I can forget about this path order exponential, it becomes just usual exponential, which is nothing but the flux, right? The integral of the magnetic field, which is the flux that comes piercing this solenoid, and which is this example that even though there is no magnetic field outside, there is, of course, some gauge field, and as I probe through one direction or through the other, I measure the flux that pierces the solenoid. And you see that when I asked the physical question, it became a gauge invariant quantity. Before it was not, because it goes from one point to the other. When A transforms, I get boundary contributions. But now I ask something physical. I ask, what's the difference between going to the left or to the right? This is physical. You can measure as an experiment, right? And then I got something, a closed loop, which was gauge invariant. So here as well, when I will start asking differences from going from one side to the other, I will close, and typical physical quantities, they are expressed in terms of Wilson loops, which are gauge invariant, whereas this guy transforms slightly at the boundary, as you saw in the tutorial. That there was some transformation matrix at each endpoints. Okay? So this is one instance where Wilson loops appear. They appear as describing the propagation of particles in the presence of the chromodynamic gauge field. Okay, actually what I have to tell, I think I should be able to finish this discussion of where Wilson loops appear and also tell about the holography tomorrow. This is probably too much for one day. I think perhaps we stop here. Are you happy? There you go. We'll stop. So,